Hello everyone, welcome to the last video of this week, and as I have already anticipated, in this part we will learn how to perform maximum likelihood estimation in the presence of missing data. So let us start with some notation. We should already be familiar with this notation, but to refresh our memory, so let y denote the complete data, the data that we would have observed in case we had no missing values. And we are assuming that y is a rectangular data set where the rows are my units, observations, or individuals, and the columns are my variables of interest, and that I have n individuals, observations, or units, so n rows, and p variables. And because I know that I have some missing values, I can further partition my complete data, my y's, in the observed and missing data part. And let R be of the same dimension of Y, so also a matrix n of dimension n times p, and Rij will take the value 1 if the corresponding Yij value is observed, and Rij will take the value 0 if the corresponding Yij is missing. And so, and more concretely, my Y observed part is formed by those individuals, those Ys for which Rij is equal to 1, and the Y missing part is formed by those individuals for which Rij is equal to 0, correct? And I will introduce a new notion here. It's the notion of the full data. The full data is the complete data together with the missing value indicator. So Y and R together form the full data. We call Y the complete data, which we know that we can further partition in the observed and missing parts, and R are the missing data indicators, and two Y and R together, we call it in the literature full data. And the full data is never really observed because I have missing observations. So what I have in practice is Y observed and R. R, I always observe it's 0, or it's a matrix of zeros and ones. And then I also have available the corresponding observed part. And as we have seen in the lecture or in the video about the formal definition of the missing data mechanisms, let's theta be the parameter of our model of interest, of the model that we pose it for Y, and psi the parameter of the missing data model. And therefore, the joint model of the full data is given by this expression here, right? And I cannot evaluate the joint model because in the usual way, because I have missing values because of this quantity here. But nonetheless, the marginal distribution of the observed data and of the missing data indicators can be obtained by integrating the joint model of the full data with respect to the missing values. And that's what I have here. Think when we have two variables, x's and y, and I have the joint distribution f x's of y. If I want the marginal of y, I integrate my joint distribution with respect to x's, correct? And so here I want the marginal joint distribution of y observed and the missing data indicators, and therefore, I can integrate the joint model of the full data with respect to the missing values. And here it's a slightly abuse of notation because I'm using, of course, this is a multiple integral because I have more than one missing value, but just to abbreviate the notation. Okay? And there are in the literature on likelihood-based methods for missing data, two factorizations of the joint full data model are popular. And the first one, the one that we will be working with, these are based on Bayes' theorem, and this just using it in one way or another. Okay, we have the joint model, and we can factorize it in different ways. Okay, and the first factorization is the selection model factorization, and we factorize in these two terms. And let us look at these two terms. This one, f of r given y and psi, is the model for the missing data mechanism, as we have seen, correct? And this quantity f of y given theta is our model of interest, the model that we have used in case we had no missing values. And so these factorizations involves two quantities that are familiar to us, and also our quantity of interest in case we had no missing data, this part here. And these are called selection models, and the name comes from the econometric literature. Ekman selection models from the 70s, they use this type of factorizations, and so the name remain the same, selection model factorizations. And this is one of the possible factorizations of the joint model for the full data. And there is another possible factorization. We will not be working with it, but I will leave its expression here. So the pattern mixture factorization, we have the joint model here as well, and we factorize in these two quantities. And the first term, oops, sorry. This first term is the density of the complete data of the Y's for given patterns of missingness. And this is the probability of each missing pattern. In fact, this corresponds more to what we observe in practice. But we will work with selection model factorizations and pattern mixture factorizations, because we have here the probability associated to each pattern of missing data. That's why the name pattern mixture factorization. And this factorization of the joint model for the full data was first proposed by Little in 1993. And just a remark, the parameters theta and psi here in these two models, they have different interpretations. Their meaning is not exactly the same, but by an abuse of notation, I have used the same, and in the literature, most authors use the same parameter, although the meaning is not exactly the same in the two factorizations. And again, repeating myself, because the selection model factorization includes two quantities that we are familiar with, the model for the missing data mechanism and the model for the complete data, our quantity of interest. We will be working with the selection model factorization. Okay, and let us start. We will need to, I will start with the joint model for the full data, and we see that under some conditions or assumptions, we in fact can perform maximum likelihood estimation using only the observed data. Okay, but let's see what we need to assume and how to reach that point. So we have our model for the full data, y r given theta, the parameter of the complete data, and psi, the parameter of the missing data mechanism. And I know that I can further, because I can partition y in its observed and missing parts. I can write, correct? And we have seen that if I want the marginal distribution for what I observed, the quantities that I observed, the y's for which the Rij is equal to 1 and the missing data indicators, all I have to do is to integrate the joint model of the full data with respect to the missing values. And now let us bring to the game the selection model factorization, okay? So I will rewrite the joint model for the full data using the selection model factorization. And I know that what I have is f of r given y observed, y missing, and psi, the parameter of the missing data model. And then I have my model for the complete data, and my complete data is y observed, y missing, theta, and I'm integrating with respect to the missing values. Now let us make our first assumption. I need to do something because here if I leave it like this, both quantities depend on the missing values, and so I have an expression that I cannot do much, or I cannot go much further. So let's start making assumptions. Under missing at random, I know that the expression for the missing data mechanism simplifies, correct? It does not depend on the missing values. Under missing completely at random, it even simplifies even more, sorry, because it does not depend on anything. But let's think about missing at random, and then missing completely at random is just a particular case. Okay, so under missing at random, I know that the model for the missing data mechanism does not depend on the missing values on psi-f conditioned on the observed values, correct? We have seen this for all missing values and parameter. And if I come here and replace in my expression, what do I obtain? And now note that we are integrating with respect to the missing values and this quantity because we have assumed that the missing data is missing at random. So the missing data, the model for the missing data mechanism no longer depends on the missing values. And so with respect to the missing values, this quantity, the model for the missing data mechanism, is regarded as a constant, correct? And as such, I can put it outside the integral. And that's what I'm going to do. And now I'm almost at the end of this part. This quantity here is just the marginal distribution of the observed values. Again, if I have the joint of f axis and y, and I integrate with respect to y, I obtain the marginal of axis of f of axis. And here I have the joint of the observed and missing, and I'm integrating with respect to the missing value, so I obtained the marginal distribution of the observed data. And so I can write as sorry. Okay. So what have we done? Under missing at random, we know that the model for the observed data and missing data indicators given the parameters is And under missing completely at random, it simplifies even more, as we have already talked about, because I have sorry, here I should put like this. Let me check what I have done. Yes. Okay, so let us recall our goal is to make inferences about theta, or to estimate theta, correct? So I can rewrite these expressions in terms of the likelihood. I can in terms of likelihoods, right? So I can regard the joint densities as a function of the parameters, and so I'm looking at the likelihood, as we have seen in the first video of this week. And so if I rewrite as a function of the parameters, and here I will leave the missing data mechanism as it is. So my goal is to, we will go now to the, we have already made an assumption that data were missing at random or missing completely at random in a more extreme case, but let's think about missing at random is not as strong as missing completely at random. And so this is the expression that I have. And if again, psi and theta, they can be vectors or be scalars. If they don't have any, if they are different, in case they are scalars, or if they don't have any parameter in common, in case they are vectors, if I'm interested in performing estimation for theta, in case psi and theta are distinct, so maximizing this likelihood to obtain inferences or to estimate theta, the only part that I need to care is this one, assuming psi and theta are distinct. I know that my MLE that results from maximizing the joint likelihood is the same as the one resulting from maximizing the likelihood of the observed data. And this is a quite powerful result. So I need to make assumptions. So I've made the assumption that data are missing at random and that the parameters of the missing data mechanism and of the data model, they are distinct. And under these two assumptions, I can obtain inferences or to estimate theta using the likelihood of the observed data. And that's a good result. And that's what I have here. This is the likelihood of the observed data. And as we have seen, I think it was in the video for, or the lecture for the formal definition of the missing data mechanism that we have talked about ignorability, and now we are in position to talk more specifically about it. And a missing data mechanism is said to be ignorable for likelihood inference if the missing data are missing at random or missing completely at random, and if the parameter psi of the missing data mechanism and the parameter theta of the complete data model, they are distinct or disjoint in the sense that the joint parameter space of psi and theta is the product of the parameter spaces of psi and theta. In the sense, as one of the authors said, that knowing theta will not provide knowledge about psi and vice versa. And so we say that the missing data mechanism is ignorable for likelihood inference, that we can use only the likelihood of the observed data if these two conditions are met. And note that we are not ignoring the missing data mechanism, but Instead, we have made assumptions about the missing data mechanism, correct? We have assumed that the missing data mechanism is missing at random or missing completely at random. And also that the parameters of the missing data mechanism, they are distinct of the parameters of our model of interest, of our model for the complete data. And as we will see in a few slides, we need these two conditions, and sometimes by an abuse of language, missing at random is called, the missing mechanism, when it is missing at random, it's called ignorable, but we know that for the missing data mechanism to be ignorable, we need the second condition, that the parameters of the two models are distinct. But in fact, and we have a simulation study in a few slides, the most important, let's say, condition is that data in fact are missing at random. If the parameters are not distinct, our inferences are still valid in the sense that they are unbiased, but they are less, or they are not efficient. We have more variability, but we will see this. And I've already said the first 3 points, and some remarks. In the first video of this week, we have talked about expected feature information and observed feature information. And there is a paper that came out in 1998 by Mark Kenworth and Gert Mullenbergs on statistical science. And they recommend that in the presence of missing data, the observed information should be preferred over the expected feature information. It's a quite technical paper, but at least we can stick with the message. And also, when we just maximize the likelihood of the observed data, and just because we have that the likelihood of theta and psi, and our inferences is to make and our goal, sorry, is to make inferences about theta. But in case that the parameter of the missing data mechanism has some scientific interest, usually there is no interest on it, but in case there is, then we should consider it and treat it carefully, even if the data are missing at random and the two conditions for ignorability apply. And also, and this is the eternal question, ignorability is a good thing, let's say. It allows us to perform maximum likelihood estimation using only the likelihood of the observed data. But remember that we can never rule out missing not at random. Missing at random is an assumption that we have to make, but we cannot verify it from our data. So there is always that ghost when we are using the MAR assumption, but let's live with it in this course. Now, let's do an example. And it's a very simple one, but just to make the point. Suppose that I have data y1 up to yn, and that data come from a normal distribution with mean mu, the usual setting, and variance sigma square. And let's assume that we only have m observations available, and the remaining n minus m are missing. And without losing any generality, I can say that I observed the first m observations. I only have one variable, right? One univariate pattern, only a single variable. And I can say that I observed the first m, and the last n minus m are missing, okay? Let me just check if I'm not messing up. And so we also, and let's assume first m observations available, and my R1 up to Rn a vector of the same dimension of my complete data, y1 up to yn. We know that because we are assuming that the first m observations are available. We know that is such that r1 up to rm, they are equal to 1, and rm plus 1 up to rn, they are equal to 0 because they correspond to the missing observations. And now let us suppose that an observation or a unit is observed with probability psi, which we assume to be different from theta, that is formed by the mean and the variance. So we have distinctness of the parameters. And I know that if each observation, each individual, each unit, wherever they are, if they are observed with probability psi, so my model for the missing data mechanism is Bernoulli with parameter psi. And so I know that f the r given psi is and because I know that only the first m observations are available, I can simplify to this form. And now if I write my likelihood for the observed and missing data indicators, I know that what I will have is, oh, and I'm assuming I forgot to say that the missing data mechanism is MAR, or missing completely at random. Okay. And now for the observed part, f, this is just the likelihood of the normal or the joint density of normal random variables, and I have the first m of them, right? So I can still write this as And now, because I've assumed or I have been told that psi is different from u and from sigma square, and that the missing data are missing at random, if I want to estimate the parameters of my data model, my mu and my sigma square, I just need to care about this part, correct? And this is then proceeding in the usual way. And we have done an example in the first video of this week for data that are normally distributed, correct? And so there is no rocket science here. I know that mu, it will be based on the available observations, the estimate of mu, and then also and call it like and it's this. And a remark, this is just to warm up, okay? This is a very simple and toy example, and in this case we have one variable, only part of it is observed, and doing likelihood-based inference, we would coincide with the results from a complete case analysis, right? Because with complete case analysis we would just also use the observed information. But this is a very special case. In the next week, we will look at data that follow like a bivariate normal distribution. We have two variables, and we can have missingness in both. And in this case, the conversation is different. But just to warm up and just to illustrate how to use the result of using the likelihood of the observed data in the presence of missing data, when missing data can be assumed to be MAR or MCAR, and that the parameters of the missing data mechanism and of the data model are distinct. And now we have here two examples, and we will study, or we will empirically study, what I have mentioned a few slides ago, that the assumption of data being missing at random is far more important than the assumption of the parameters of the two models being distinct. And I have considered here a situation that, again, I only have a random variable that I'm assuming to be, I have random variables y1 up to yn, and they follow a Bernoulli distribution with parameter theta. And then my missing data indicator, which in this case will take value 1 or 0 if y Ri will be 1 if yi is observed, and will be 0 if yi is missing, so they are vectors. And again, Ri follows also a Bernoulli distribution, but note that the parameter of the missing data mechanism is equal to the parameter of our data model. Clearly, data generated in this way, it's a missing completely at random, does not depend on what is observed or on what is missing, does not depend on y's, right? Because there is only one variable, so if it depends on y's, is missing not at random. But here it's clearly missing completely at random, does not depend on the y's. And we are breaking the assumption, or violating the assumption of distinct parameters, right? And in this case, I can write the likelihood that we have been. This is my likelihood, and I know that when the parameters are distinct, I can just use this part, correct? I could ignore what comes from the missing data mechanism. But here I'm including it because I want to do the exercise of comparing it to the situation where I ignore it. So I know this is similar for the missing data mechanism to what we had in the example of the normal distribution. I'm saying that the random variables they follow a Bernoulli distribution. So an observation is observed or is available with probability theta, and this is exactly what we had before for the normal example. And then this is, I know also, I'm assuming also that I have missing observations obviously on Y, and again, without losing generality, that the first M observations are available and the remaining N minus M are missing. And so this bit here in green corresponds to the likelihood of the observed data. What is in yellow here is the contribution of the missing data mechanism, and here is the likelihood of the observed data. And because I know that only the first M observations are available, I can simplify, and I end up at this expression. And okay, I want to make inferences about theta, so I know how to proceed. I compute the log likelihood, I do the derivative of the log likelihood with respect to theta. This is a very simple case, and I obtain that the maximum likelihood estimator is based, when I take in consideration both the contribution of the observed data and of the missing data mechanism, because I know that the parameters are not distinct. That's the expression that I obtained for the maximum likelihood estimator. If I ignore this part, it should be red. Okay, so if I ignore this part, what I obtain and ignoring this part here, so if I just ignore that the parameters are not distinct and say, okay, I will just use the likelihood of my observed data, I will just, I have an inability with the eraser of the iPad. I will just use this bit in the red squared, correct? And this would lead me to this MLE. So this is the MLE just considering the observed data, and this is the MLE considering the observed data and the contribution of the missing data mechanism that I know that I cannot ignore because the parameters are not distinct. Okay, and what I have done is, okay, I will simulate data. So I have simulated 1000 data sets. Each data set has dimension 100 and the true value for theta is zero point 0.3. And then I have simulated data according to what I have here for the y's. They are Bernoulli with parameter 0.3, and then an observation is observed also with follow the model. The probability that an observation that a y is observed is zero point 0.3. And what I have here in the left are the histogram. So I have simulated 1000 data sets and I have computed the MLE that I have obtained by considering the likelihood of the observed data, this part here, and on the left is the likelihood of the observed data times the contribution of the missing data mechanism. And the vertical red line is 0.3 is the true value of theta. And we can see that when we consider the full likelihood that it's the correct thing to do in this case, because the parameters are not distinct, my inferences are unbiased. But when I use the observed data likelihood, they are also unbiased. But if you look carefully here on the scale, on the right, when I only consider the observed data, I have much more variability, right? And this aligns with what we have been told, that when we violate when the assumption of distinct parameters is violated and we only use the observed data likelihood, our estimates are still unbiased, and we are checking this or observing this, but they are less efficient. And in fact, compared to this situation, we have more variability, correct? But now let's do another exercise. For this same data, I already have 1000 data sets, correct? I have simulated data from the y's from a Bernoulli with parameter 0.3, but now my missing data, my missing mechanism is missing not at random, because I have considered this model and it depends on y's, and y's have missing values. So the missing data mechanism is missing not at random. And now I'm using the likelihood of the observed data. That's the only thing that I'm using. But remember that before, by using the likelihood of the observed data, my inferences, they were not efficient, but they were unbiased. Now that the parameters are distinct, but we are violating the assumption of the missing data being missing at random, my inference or my estimates, sorry, it's not my inference, my estimates, they are biased, correct? Here I have the true value and most of them are to the right. So we have checked empirically for a very particular example that, in fact, we know that the missing data mechanism is ignorable for likelihood inference if data are missing at random or missing completely at random, and if the parameters of the missing data model and of our complete data model are distinct. But the more important assumption is data being missing at random, and that's why some authors call missing at random ignorable missing, although we know that we have an extra condition. In fact, this extra condition, we still obtained unbiased estimates. Okay, and that's it for this week. In the next week, we will look at a further example, the one that I've already mentioned about bivariate normal distribution with missing values, and see how to play with this likelihood of the observed data. And then we will start learning about the EM algorithm, that is an algorithm that is tailored for estimation, for maximum likelihood estimation in the presence of missing data that sometimes simplifies our the calculations that we have to do, but that's for next week. Thank you and enjoy your week.